Now I'm adding this to the beginning, reminding you that you could go over here to the right lower corner and select a faster speed for this. It's somewhat long. 1.25 would cut it down by 10 minutes, and I think you could still get the information needed. So with that, let's get started. In the last section that we will be covering in Math 1108, 8.3, describing and analyzing data. The textbook material gives a very good background for all of this, but here it's summarized in these PowerPoint slides. So our objectives to calculate numerical descriptions of data, such as the measure of center, standard deviation, and percentiles. Displaying data in a clear and informative way is certainly an important and necessary step in research. Just as important is describing the data numerically so they can be compared and analyzed. Background. Now, we're going to look at three things that are sort of easy. They all start with the letter M. The first, and we've done a little bit of this in the past, the arithmetic mean, in a sense, is an average. The mean is the sum of all data values divided by the number of data points. So formally, the formula of population is, now this funny shaped U is a Greek letter, I believe it's mu, and here are all your data items listed, and N is the total number of data items, and that's what you divide by. So a common one is if you had 10 data items, you'd add them up and you would divide by 10. So X sub I is the first one, and I to the nth data is, again, the number of items of data in your population. Now, this is the whole population. Now, generally, you can't sample the whole population, and you're going to take, in a sense, a sample that is a portion of it. Some from here, some from there. You're going to do a part of the whole. Now, this gives you what is called the sample mean. And this formula, you should be writing these in your notes, is X bar, is done pretty much the same way. Take all your items of data, add them together, and then divide by the number of items in your sample. So for example 1, take a moment. These are our items of data. This is the number of sick days employees at this insurance agency took last year. So there were 1, 2, 3, 4, 5, 6, 7, 8 items of data. So this would be the whole population in a sense, but it's done in a similar way as a sample. The solution, of course, is that you add them together, as we see here, and then divide by 8. So the X with a bar above it, this is the symbol for the arithmetic mean of a sample, that is the average. And it turns out to be about, and we approximate, we round off, 8.9. Now, another M word is the median of a data set. Now, once you put your data from lowest to highest, and you count, in this case there were 8 items, you sort of go to the middle, and what value is in the middle? Well, that would be your median. Sometimes it's close to the mean or average. Let's look at an example. So here is the max score of oxygen that one's body can transport during exercise. And I'm assuming they have some sort of device that can measure this, and you get these values. And there were 12 women involved. So how would we find the median? Well, the first thing, and if you have one like this as part of your practice and certify, you're going to have to list them in numerical order from lowest to highest. Fortunately, they do that here. Now, we said there were 12. So 1, 2, 3, 4, 5, 6 on, in a sense, the top line, and then there's 6 on the bottom line. Now, since it's an even number, the median would be between 27.0 and 27.1. So if it were odd, it would be that 7th place here. But since it's even, so how do we find out what the median is? Well, when there's an even number like this, and they're going to show us, we add these two together and just divide by 2. So we take the average of just these 2 that are sort of in the middle. And I can see it's going to be 27.05. And there it is. So even though this is not a physical number in the list, it is the median. And why? Because we had to do this because it's an even number of data items. If it were odd, we would just take that middle one. All right, let's go on. And again, we're saying what we said. That item is not in the data set, but it gives you what, in the sense, is the median. All right, another M word, and this one is relatively easy. It's the mode. Now, the mode is the value in the data set that occurs most frequently. So we'll use the set of data here of all of these items, and they're kind of in a kind of a bluish color. We want to find the mode. Now, sometimes as you look at data, and let's just note these words here. If there's just one value that's used most often, we say our data reflects the unimodal, uni being the prefix for one. If there were like 2 that had the same value compared to all the others and they were larger than the others, this would be bimodal. And if there were a number that had, large numbers compared to the rest of the data, we would say it would be multimodal, that is many. And then there are cases where the items are just used once. There would be no mode. So as we look at, and again, you're writing this in your notes, example 3, you don't have to write all of this down, but here someone is looking at cell phone cases and they're wondering, is there a mode of the color of these cases that are selected most often? And you might say, well, how can you possibly do that? Well, if these were lined up alphabetically, that might help, but they're kind of like scattered. So again, some sort of technique here, and you might do something like this. We're going to say lemon. Let's say that that's a 1. And then you look through here and see where lemons are. There's a 1, a 1, a 1, lemon. Okay, so we have a number of those. Now you take gunmetal. Well, let's say gunmetal will be a 2. So we want something that will stick out. Now you could also color code these maybe. Gunmetal, and I'm going to pause while I do this. And you may not have to do something like this. You can use another technique. But as I got to the violets and I was placing a 3, I have 1, 2, 3, 4, 5, 6, 7, 8, 9. So that's the most you're going to have of any, as I kind of scanned the rest of them. So the mode of this set of data would be the violet. And again, whatever method you choose to recognize them, you could have put, you know, shade them out or whatever. I think these numbers work well. Okay, let's go on and see what they say about this. So we did pick out the right color, violet, and this set would be unimodal. Now in example B, we're looking for the mode in terms of jersey numbers. So as we look through them, and there isn't a number that's repeated, so this would be no mode. Now, ages of children at a community playground one afternoon. So as we look through these, I see a 4 there, a 4 there, and a 4 there. And I see a 7 and a 7 and a 7. So there are 3 of 4 and 3 of 7. So those would be the mode, and this would be bimodal. Now, number of ATM withdrawals per hour at the downtown branch of a university bank. Now, this one's kind of tricky the way it's worded because it's per hour and these are all different hours. So if they said during the day here instead of hours, then you might pick out that, you know, there's 13, 13, there's 9, 9, there's 14, 14, there's 10, 10. So this would be like multimodal, but they're saying per hours. So again, you don't have any data to see like within the hour. So this one's a little tricky. So this one you can't find a mode for based on that they want it by the hour. That one was tricky. When I looked at these earlier, I had problems with that one myself. All right, let's go on and look at the answers. So we did part A already, Violet, unimodal. Part B, again, the Jersey numbers, no mode. And then in C, we had 4 and 7 occurred equal number of times. So this would be bimodal. And letter D, and they're telling you to be careful here, since each value occurs the same number of times within the hour, there is no mode in this data set. That one's a little tricky. Now, a word we'd like you to add to your vocabulary is what we call an outlier. Now, normally when we look at data here, and if we were to put our data on a curve, and it might look like this, with there is your median, and that might be the mode also. But the data would sort of be equal on this side to that side, and we call this a bell-shaped curve. Now, other times you might have a curve that looks like this, where it's sort of skewed to the left. Or you might have something that looks like this. Skewed to the right. And also you might have a series of data where, your scores are, let's say, if you were to do a kind of a thing, and it would be like, and then you might have a person or a value way out there that really seems away from your central data. Now, by averaging in, this would move this, but if it's considered what we call an outlier, you might say, well, I'm going to ignore that. There might have been something wrong. Well, a teacher, for instance, giving a test, and he's taking the students' scores on a test. Well, generally, these people came to class, did the homework, and scored on the test. But this person wasn't attending, didn't do the homework. Should that result, but came for the test, should that score be considered part of this average? Again, you might or you might not, but this is considered an outlier, something that is beyond. Now, often what teachers might do, if they get one like way over there and way over there, they won't count these high and low, and they want to see what's that central tendency like. And these here would be considered outliers. Okay, we're getting ready for our next example, and we'll give you a chance to work on this here. For example 4, finding the mean, the median, and the mode. So we'll pause here, let you go through them, and then see what in fact you end up with. Now, how many items of data? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, now we're just going to average these up, add them all up, divide by 11. That will give you the mean. You're going to then line them up numerically, and your sixth item of data, which is 5 on one side, 5 on the other, because it's odd, that will be your median. And then you're going to look to see if there is a mode. Again, when they're lined up nicely, you can pick that out. In fact, I almost see it here. A 15 and a 15 might be, but I will pause and work it with you. So 37.4 for the mean. Now again, lining them up. In fact, if I had an example like this, what I would have done is initially put them numerically. Kind of look over, get the lowest number, and you leave spaces so you can line things up. So our median then is 26. We didn't have to divide it by 2 because it's an odd number. There are 5 on this side, 5 on that side. And I see the 15s look like they're repeated. So there's the median. And the one with the most often used is 15. Okay. Now, what they're saying here, and I'll go back to this slide so we can see it, is that even though 15 is the mode, with this range of values, that doesn't really give you a good value for, looking at this data. While the mean, the average of them might be the better. So again, looking at your data, what does it mean? What does it tell you? We're just looking at numbers and defining vocabulary, and we'll continue with our work. Now, here's a skill check. Again, if I were doing this, I would write them in ascending order first. And there are, let's see, 2, 4, 6, 8, 10. So in figuring out the median, we're going to have to average our 2 middle ones. And let's see what we get here. So the mean then would be 11.7. But our median, and we got 2 11s in the middle, we had to divide that by, add them together, divide by 2, so it gave us 11.5. And our mode, it's bimodal. We have an 11 and a 12. Okay, let's look at another vocabulary word and fit this into our study. The range. The range is the difference between the largest, that is your maximum value, and the smallest one, your minimum, in a data set. This tells you the distance covered between the first, which would be the minimum, and the last, the maximum. Now, what is the formula for range? And you want to write this down. Without range, you would take the maximum value, this would be the larger number, subtract the minimum value, the smaller number, and then that would give you your range. Take a moment, write this in your notes. Again, these could be quiz questions. All right, now we are looking at some new data here. And again, you don't need to find the average, the mean. You don't need to find the mode. You don't need to find the median. But as you look at this, we're talking about 12 semesters. We're looking for the smallest number. And as I scan that, it looks like it's a 5. And the largest number looks like it's a 54. So 54 minus 5 is going to give me 49. So the range of A, doing it from the top of my head here, is 49. Now here's the number of shoppers at a gas station, and there's 7 items. what is the largest here? Well, the largest looks like 1054, and the smallest looks like there's two of them, 1005. So when I subtract them, I also get 54 minus 5 is 49. So both of these are 49. But let's just put this on a number line here. This is the number line. And here we have a 5. And here we have a 54. And the range then, as we said, was 49. So our numbers here are rather small. Now for this one, here we have a number line, and again, if this is 0, then we're up here in the hundreds and thousands there. And this is where we're going to have 1005 and 1054, and this is going to be 49. So here we see, with the data that we're looking at, this range is quite large for the values that you're dealing with. While in a sense of numbers, this range is rather small, but it's still the same range. So we want to have another tool that will allow us to study data, and that's what we're building up to here. So let's go on, clear this up. And that one was straightforward. And that one is straightforward. But we did give you some background on it. Now, we're finally getting to something really technical and helps us to understand the data that we're studying. And you may have heard of this before, standard deviation. Now, what does it mean? Well, it's looking at a set of data. We analyze the numbers that we're working with to figure out where the number we are studying fits into the overall population. And this formula is for the whole population. Now, we'll take a look at the next one, which is the one that we most commonly use when we just have a sample. Instead of the whole population, it's a sample. And what does it refer to? Well, again, it's the sum of these. And what did we say this was? Well, this x sub I is an item of data, one item of data. Now, we know that x bar is the mean or average. So what we're doing is we're looking at that specific item of data, and then we're going to subtract it from the mean. Now, in some cases, it'll be more, and that'll give you a positive value. Sometimes it will be less and give you a negative value, but you're going to square that. And you do that for all your terms. So all of these numbers always end up positive. And then this differs from the previous one in that we subtract a 1 from our item number of data. So if we had 10 items of data, subtracting 1 would give us 9. So we add all of these together, and that will give us the sum. Now, it might look like you're going to multiply this times that, but you don't. You just take all of these items and add them together, and then divide by 1 less than the number of items of data. And then you take the square root of that, and that will be your standard deviation. And we'll tell you how that fits in, how we look at it as we go on here. So here we want us to calculate standard deviation by hand. Now you might try one or two of these. I'm not going to ask you to do them all. So the first thing we have to do is find out what the mean of this would be. And our sample is 9. So once we find our mean, which is 20.67, okay? Now, let's just do one together here so we see where this data comes from. So our item of data is 17, let's say. So we have 17 minus our mean, which is going to be 20.67, that we're then going to square. All right, let me put that into my calculator and we'll get back. Okay, when I did the subtraction here, I got a negative 3.67 that I squared. And again, anytime you square a negative, it's going to give you a positive value. Now they want you to round this off to 2 decimal places. So with an 8 in the 3rd decimal place, I'm going to drop these 2 and make this 6, a 7, where you see I get the data from here. And I'm going to erase this part here as well, now that you see where we've got it. Now you need to do that for each one of these items. That's why it's a little tedious, but if you can at least do this one, that'll be good. All right, now we're going to go on. And the nearest hundredth, we're rounding off. Now here they give us the table of these items of data. So they're all listed here. There is 17. When we subtracted it from the mean, we got this. When we squared it, we got that. Now this should go, of course, up here now. Now we had to do that for the whole table. As you can see, this is quite tedious here. Now you're going to add all of these up and you end up with this. Now just think, if you're doing this by hand and if you make little errors along the way here, this is not going to end up correct. So that's why it's so useful to be able to use a software or a calculator to be able to do this. Now we're going to take this number and put it in this formula. This is where our sigma goes. Going back one, let's write that there here. Get my pen. So this is going to be 96.01. Now we can move it up. All right, so this top part is the sum of all these individual items of data. Now we're going to divide it by 9 minus 1, 8. And let's see if we can do that. So I'm going to put in my calculator here. 96.01 divided by 8. Now I have a value. And my calculator, I'm going to take the square root of that. So I go second function, square root of 12, and then what I got there. And I end up with now, because this is our standard deviation, 3.464, And since our third value is a 4, we're going to drop it. So this is our standard deviation. And you might say, well, what does that mean? We're going to go over that with you right now. And they're rounding it to 3.5. That makes it a little easier. Okay, good. Want to be sure we knew where we got that from. Now, as we wind up our study, I want to bring you to what is called the empirical rule. And this deals with standard deviation. And what it states that in general, once you find the standard deviation, we said that was going to be 3.5, and we had our mean, which was the average of that data we're working with, which would be right there in the middle, that if your standard deviation is 3.5, that is, if you added a positive 3.5 here, and that would be up to this red line, and you subtracted a 3.5 from this line, you should expect that of the data that you're studying, that would be 68% of the population within one standard deviation. That is, to this side and to this side. Now, I would suggest you just make a rough sketch of this bell-shaped curve, and then in the middle, that is your mean. Or it could be your mu, if it's the total population. That's what they're showing here. Now, how about two standard deviations? Again, plus 2, which would be 7 this way, and negative 7 this way here. What percent of the population would you expect within two standard deviations? And the answer is 95%. Okay. And then how about three standard deviations? A negative 3 standard deviation, a positive 3 standard deviation. This would be 99.7% of your population. So I recall when I taught biology years back, we would say, where does your data fit? What is the probability? And we've talked about that already. And then if it's within 3 standard deviations, that's pretty much your whole population. If it's within 1 standard deviation, that's going to be 68% of your population. Now, I don't expect you to remember all this, but hopefully you understand where it came from. And as you do your practice certify, you're going to be able to have the background to be successful. All right, let's go on. Now, as we go into example 8, we're going to use the empirical rule and kind of watch this and take down some notes. You're going to need your bell-shaped curves here and standard deviation to do this one. Now, we're at a hospital emergency room, and the waiting time we're assuming is a bell-shaped curve. The data reported a mean of 116.9 minutes. Now, they could have had nice whole minutes here, but they're giving you the decimal. And the standard deviation of 56.1 minutes. So that means 68% of your population would be within 1 standard deviation, adding this to that and subtracting this from that. Now, they want to identify the range of waiting times that 95% of the patients are likely to experience. Well, this one's sort of easy because we're going to take 2 of these and add it on this side here, 2 times 56.1. And on this end, we're going to subtract 2 of those, 56.1. And that would give you the range of waiting times. That one was easy. Now, this one's more challenging. Estimate the percentage of patients that will wait 2 hours and 53 minutes. Okay, so you have to see where this would fall on that bell-shaped curve. Now we have to change that from hours to minutes. So this is going to be 120, so 173 minutes. So in here, where is 173 minutes? Well, rather than my drawing it out, I'm going to let the book do that because they do a nice job. And let's check it out here. So we did that already. And then it will be from 4.7 minutes to 229.1 minutes. 95% of the patients. We're just adding 2 standard deviations to each side of the median. Now for this one, we changed it to minutes, which was 173 minutes. And if we subtract that from the median, we add 56 minutes. So we're going to do 56 minutes, which brings us to this point here. And that would be about 34%. Here we know this is 50%, this part. And if you add that, then it's 84%. And that would be about 84% of the patients. Okay, again, some of these are challenging, but let's go on. Our last 2 items that we're going to look at, vocabulary words, is percentile. And here it's the data, think of it on a number line, of 100 equal parts. And we'll go over that. So let's look at this. Sarah received her scores from taking the placement test, and she scored in the 61st percentile. Now again, if we're looking at a number line, 61st percentile is right about there. Now, what does that mean? Well, she correctly answered 61% of the answers on the test. Is that what that means? That she's in the 61 percentile? And the answer is no, not for this one. That doesn't mean that. That 61% of the people taking the test score the same as Sierra. Ah, this is yes. This means that other people taking a test score, when they got that test score, she was at the 61 percentile compared to the other people that had that same test score results. That Sierra's score was at least as good as 61% of the people take. This is another yes. Yeah, she was up there. This is where she was. Sarah missed 39% of the test questions. No, that's not what it means. Percentile is position of you compared to others. So whether that test you got a 50% on it, or whether you got a 90% on it, whatever score you got that these other people got, you were with the 61 percentile of that group. Okay? So it doesn't tell you the test score. It just compares you to people in that group. That's what percentile does. Okay, let's go on. And there they are. I kind of pause to see this. We're running a little longer here. Now, quartiles. Now, if we take a number line and we can divide it up into quartiles, that is quarters, this would be the first quartile, the second quartile, the third quartile. This is comparison of where you would be in general groups. This would be, in this group here, 25%. Make a 5 there. This would be in the another 25, another 25, another 25. So to be in the third quartile, that is 75%. By definition, the second quartile is the same as the median. So this is a vocabulary word related to percentiles, but this is in quarters. All right, let's go on and see where they're going with this. Now, on Carl's recent standardized test result, the picture graph. All right, they're giving you some sort of a picture graph, some sort of circle or something, that he was above the first quartile, the third quartile, I should say, in language arts. His classmate Asher was at the 70th percentile. So since he was above the third, he did better than this. While Riley said hers was the 79 percentile. Which of the three had the best language arts score? Well, you know, this person didn't, but this was above the third. This was above the 75%, so this was above the third, but we don't know particularly where these two were. I could spend more time, but we're running way over on this, and again, you know who did more poorly, or not too bad, but otherwise we don't know. And you can pause and read this. We don't know for sure who did because of what we just said. Okay, now Excel is another software program. I'm not sure we're going to be using it, but if we do, we'll give you some specifics on that. And with that, we'll wind up this rather long last lesson.